Hey everyone. Thanks so much for having me. Today I'm going to talk about our coding model at Cursor, which is known as Composer. We're going to talk particularly about the second version of Composer, Composer 2.5. This is a team effort. I am just a contributor to this group. We have about 40 folks working on the development of these models. I'm going to give you an overview today about how it works, kind of at a bird's eye view and a sense of where we're going with these models. So first off, the goal of Composer was to build a really strong coding model. We wanted a model that people would use in everyday use. And over the last several months, these models have gotten very strong at lots of different benchmarks. Here's the current performance of our Composer model. It nears the performance of models like Opus and GPT 5.5. At the same time, the model combines this intelligence with both efficiency and also kind of token cost efficiency. And in practice, a lot of these models should be thought of kind of being graphed on this two-dimensional axis, where you're looking both at intelligence, but also at either the price or the speed or the amount of tokens that these models use. Generally, we know that models that kind of talk for longer, think for longer, will perform better. And so we're aiming for a model that's practical, where you can use in kind of an everyday setting. So the way these models work is that they run this agentic loop. The model is given a set of tools that it can choose from. And it's going to basically talk to itself, decide which tools to use, and then call them. It interacts with your coding environment by reading files, by searching for new files, by producing changes to the files that exist, and increasingly by using complex shell commands to run or babysit jobs. But I think probably you all know this at this point. The last several months have seen an incredible explosion in the use of coding agents. It's become kind of the killer app of AI generally. And we've seen this at Cursor as well. So even like a year ago, a lot of our use was from people using tools like Tab or writing code manually in the IDE. And then at the beginning of this year, we saw a massive blow up in the use of these agentic tools. And honestly, now most developers at Cursor are going to change our own code base primarily by using the agent, by kind of having it check things, by checking PRs, by writing huge amounts of code, increasingly for doing things like helping run experiments as we go. So this becomes kind of the central way that people use these tools. So we were trying to train kind of the best model we could. And we think about this as having kind of three specific goals. First, we want the model to have as much general knowledge about coding that we could. We want the model to have this information quickly so it can pull it up from kind of its memory and its weights and do well at various tasks. We're also increasingly interested in not just solving simple tasks, but solving the complex tasks that people expect these models to work on. This means working for a long time and trying to solve tasks that go beyond just writing code to other aspects of software development. Finally, it's important for us that this works well on the real sorts of tasks that people ask. There can be a tendency to look at kind of puzzle type tasks or tasks that kind of are like from coding competitions, and they look quite different than the tasks people actually want when building software. So let's talk about these three areas. So first, knowledge. How do we get a model that starts very strong at coding and make it even stronger for the tasks we're interested in building models for? So the way we do this in practice is we start with a very strong base model. There are many good open source models available now that you can begin with. We chose to use a model called Kimi K2.5. It's quite a large model. It's about a trillion parameters. And it has some interesting properties that make it efficient to run. For instance, it has multi-head latent attention, which allows us to serve the model efficiently. We did some comparisons of this model versus other open source models, and we found that actually there's quite a few of them that are really good starting places for building strong models. This gave us a good place to begin the process we're interested in. But even starting with this model, we wanted to specialize it even more for coding. So to do this, we built a large corpus of coding-specific data, and we ran a large continued pre-training. This pre-training uses lots of compute and translates it into knowledge about the tasks that we want the model to do well on. We found that even kind of starting with a good model, we could kind of continue pre-training this and reduce the loss of the model on these tasks. We do this in kind of a standard three-phase setup. We begin by doing additional short context pre-training. We then switch to long context pre-training, and finally to SFT tasks that look closer to the agentic task we're interested in solving. Long horizon is particularly important for coding because coding is one of the few areas we've seen where really it needs very, very, very long context in order to solve a lot of problems. We also found that doing this continued pre-training actually improved the model at the end of the day. So we looked at 3 different checkpoints, each with different loss, and we found that after taking them and running RL, we were able to see an improvement in our final reward based on how much knowledge the original model had. Once we've done this, we switch to long horizon reinforcement learning. The goal here is to find a collection of hard tasks that we would like to solve by really running RL in practice. And we do this by finding tasks that simulate user queries that people would ask in practice, and then kind of running a thought experiment of running these offline and seeing how well we can do. So we start with a variety of different task types. So we collect a bunch of different problems. Some of these are adding new features or having debug requests, but some of them look like building documentation or managing or babysitting jobs. These tasks vary greatly in difficulty, and the kind of whether the model will be able to solve them or not will vary as we run training and the model gets smarter. The RL process itself looks like kind of a toy version of how you might imagine RL working. We literally just set up a Docker container. We then run, let's say, 32 different attempts at trying to solve the problem. We see which of these succeeded and which of them failed, and we update the model to be closer to the ones that worked. Now, that's easier said than done. As I mentioned earlier, these tasks have become increasingly long with hundreds of tool calls and hundreds of thousands of tokens in order to solve them. Different attempts at the problem will require much different length and call very different tools. And so you have a heterogeneous group of these different rollouts that you have to manage. Much of the interesting work in the infrastructure of these systems is kind of making this work efficiently, managing asynchronous RL, and kind of dealing with these real-world rollouts. Once you get this right, you want the model both to work well in terms of coding intelligence, but also to have behaviors that the user would actually like. So one thing that we do is we incorporate penalties that try to force the model to behave in ways that kind of fit user expectations. So one of them that we've written about is this kind of length penalty. And we work with a kind of non-linear length penalty, where if the problem is easy, we'd like the model to solve it quickly, kind of find an answer right away, give it back to the user. But if the model's hard, we'd like it to kind of keep on going. If it can't figure out the problem exactly, we'd like it to use more tokens, call more tools, and try to solve the problem in practice. And we found that by doing this, we can make a model that much more fits kind of the user's experience and makes it more pleasant to use in practice. We run a lot of evaluations for these systems. One interesting thing we found is that the performance of these models will increase kind of predictably over time. The more problems we feed to these systems, the better they will be. One thing that people have kind of mentioned in the academic literature is that there's a worry that RL just makes the best solution better, but hurts the model's kind of general distribution. We didn't really find this in practice. At kind of the scale we're running at, the model continued to get better, both in its best solution, but also in the kind of top K solutions for the model itself. So it just seems to get better overall. Finally, one of the most important parts about building these models is coming up with good evaluations. And I think this is a key aspect of coding systems, but all sorts of other systems you might build. And as part of this, we built our own evaluation to try to target realistic tasks that we thought mimicked user experiences. And we call this this benchmark Cursor Bench. So Cursor Bench has gone through many different iterations. We're up to our third iteration of the system. And we use Cursor Bench both to evaluate our own models, but to determine how good other models are in our product. So we do about just as much benchmarking of systems like Opus or GPT as we do with our own models. And our goal for this benchmark is that we wanted it to remain uncontaminated, so not have things that were available on the web, cover a range of different use cases, and also test more than just functional correctness. So did it actually produce working code beyond kind of just passing a unit test? And so with these three goals in mind, we kind of developed this benchmark. And one thing we found that I think is quite interesting is that it looks quite different than the benchmarks you'll see kind of in the public. So for one, the actual code that's produced is significantly longer than these other benchmarks. There's often not like one little trick that will solve the problem, but actually like a whole PR that has to be produced. But at the same time, they're well less specified. So there's much less kind of user input in terms of what they want. And because of that, you don't have a kind of one-to-one correspondence between a kind of an input and an answer, but you have to work with the kind of real uncertainty that people expect in these systems. So here's an example of what one of these look like. I won't go through it in too much detail, but roughly you have something like this at the bottom, where the user is kind of using informal language. They're making references to other things in their code base. They might even be making references to third-party systems like Datadog. And at the same time, they're kind of giving a kind of bunch of stuff that you have to reference in order to get this right. This is not saying that other benchmarks aren't useful for these sort of tasks, but we think this measures something more kind of what we're targeting at as a kind of final model. Cool. And it's worth noting that this benchmark does separate out the different models that we see in practice to a much greater extent than some of the academic benchmarks we've seen. And I think there is actually quite a wide gap between the kind of best models for coding and some of the other models that people use in practice. So let me end by just talking about our recent version of this model. So we released a second version of Composer 2 last week. This just came out, I believe, Monday last week. And in this model, we make several kind of changes to the core formula. First off, we did much more training. So starting from the Kimi base model, we do about 80% more training on top of that base. So I think some people think that this kind of post-training is just like a small step on top of an already good model, but it's actually quite a large amount of additional effort. And that's both from running this mid-training and also running this very large-scale RL process. We also added a couple interesting wrinkles to our formula. So one that I'm very interested in and have been working on is to try to move beyond kind of RL on entire sequences to try to do more targeting of the reward signal. So I mentioned earlier that we're running RL for hundreds of tool calls and hundreds of thousands of tokens. But then at the end, you just get a reward about how well you did on the task. So there's kind of this very sparse signal getting back to the model itself. One method we've been looking at is a method called text feedback. And the way this works is that if we see an issue on one specific part of a very long rollout, we can then target a kind of textual correction to that specific mistake. So in this example here, the model has made a kind of syntax error by calling the wrong tool. And we kind of feed back in a kind of information that tells it how to do it better. The model can then interpret that, and it will actually change the probability of the specific mistake it made. And we can basically compare the probabilities before and after and use that to get an update signal to the model itself. So this gives us a kind of first pass of a kind of more targeted reward to the model itself. The other interesting thing we saw was that as these models get much smarter, it becomes harder and harder to find problems that are challenging enough to kind of stump them. It's important to find these problems so that the model can get smarter as it trains. So one thing we did in this run is we created a lot of synthetic data through transformations of realistic coding environments. So one transformation we used is we would delete kind of features of the underlying code base and have the model try to restore them. So we basically give them a query and ask them to restore some aspect of the problem. We found that this worked very well in producing hard, challenging problems for the model, but it also led to some interesting hacking. So one thing we found was that the model got good enough that it could do things like reconstruct Java bytecode into the code itself. And by doing that, it was able to find random artifacts that were left in the repository, use them to find the original code to get around solving the original problem. So I think increasingly kind of figuring out ways to kind of stump RL in order to keep on training models will be an interesting problem going forward. Okay, thanks so much, and try out Composer 2.5.